Hello everyone. On this video I'm going to talk about multiples, factors, prime numbers, and prime factoring. Before we go any further though, I want to bring up the concept of a domain. The dictionary definition of a domain is the territory controlled by a government or ruler. In our case though, the domain means that group of numbers we are considering for our discussion. Usually when we talk about multiples and factors, we restrict our discussion to counting numbers. So the set of counting numbers will be our domain. But multiples and factors also apply to integers. So I want you to keep that in mind, and I will remind you of that at the end of this video. Prime numbers and prime factors deal exclusively in the domain of the counting numbers. If you are unfamiliar with the definition of integers and counting numbers, then I recommend that you review video 2 on the different number types. Let's start with the counting numbers, and I'm going to lay them out in a column for display purposes. Remember that this is infinite in the positive direction, so I'm only going to be dealing with just enough of the set of counting numbers to give you an understanding of the concepts. Let's take our counting numbers and multiply each of them by 2. We have the following set of equations. The numbers which are the products of these multiplication equations, 2, 4, 6, 8, etc., are said to be the multiples of 2. All of those multiples are said to have 2 as a factor. So 10 is a multiple of 2 since 2 times 5 is 10. Both 2 and 5 are factors of 10 since the product of their multiplication is 10. A couple more examples to make sure you understand. 6 is a multiple of 2 since 2 times 3 is 6. Both 2 and 3 are factors of 6, since 2 times 3 equals 6. Is 5 a multiple of 2? It is not, since there are no counting numbers that I can multiply 2 by that would give me a solution of 5. Now let's consider the multiples of 3. I'll get the multiples of 3 by taking each counting number and multiplying it by 3. Let's also write down the multiples of 4 and 5. One of the things I would like you to notice is that every number has itself and 1 as a factor. This makes sense. 1 is the multiplicative identity, so by definition, any number multiplied by 1 is that number. Some numbers, like 12, have a lot of factors. In the case of 12, there are 6. 12 has 1, 2, 3, 4, 6, and 12 as factors. The factors can be paired. 1 goes with 12, 2 with 6, and 3 with 4. These pairs are the numbers multiplied together to get 12. Not surprisingly, these are called factor pairs. There is no specific notation for a factor pair, but I'm going to write them like this so that it is clear to you that these two numbers form a pair. Let's try one more example before we move on. What are the factor pairs of 24? Pause this video and take a moment to figure out the answer, and then resume the video. The factor pairs of 24 are 1 and 24, 2 and 12, 3 and 8, and 4 and 6. There is no specific order for the pairs. By that I mean that 4 and 6 is the same factor pair as 6 and 4. The order in which we present those two numbers is unimportant. This is because of the commutative rule of multiplication, which we learned about in the last video. How did you do in that example?
Nailed it!
Wonderful. If you had some difficulty, then I think it will become easier as we go along through some more factoring later in this video. Next, let's discuss prime numbers. If a counting number has only 1 in itself as factors, then it is said to be a prime number. So 2 is a prime number since the only factors of 2 are 1 and 2. 6 is not a prime number since it has the factors 2 and 3 in addition to the factors 1 and 6. So let's go about finding some prime numbers. First, let me write down the counting numbers up to 100. By convention, we don't consider 1 as a prime number, so I'm going to eliminate that number from consideration. So let's consider the next sequential number, which is 2. As I said a moment ago, 2 is a prime number since it has only 1 in itself as factors. I'll circle it to indicate that it is a prime number. Then let me put a red mark on all of the numbers which are multiples of 2. These numbers cannot be prime numbers because they have at least one factor besides the number 1 in themselves, specifically the number 2. Let's go to the next sequential number which is not crossed out, namely 3. 3 is also a prime number since it has no factors besides itself and 1. Let's circle 3 to indicate that it is a prime, and then put a yellow mark through all of the multiples of 3. Again, these numbers cannot be prime since they have 3 as a factor. The next number which is not marked out is 5. It is a prime number. Let's circle it and put a mark on all of its multiples. If I proceed in this sequential manner, then I can find the prime numbers and eliminate the multiples of those primes. Let me do this for all of the prime numbers between 1 and 100. The circled numbers are the prime numbers. I used to recommend to my students that they remember the first 10 prime numbers. That knowledge comes in handy when you do factoring, as you will learn. The last topic of this video is prime factoring. Prime factoring is the process of breaking down a number into its factors and then breaking those factors down into their factors until we have a string of factors, all of which are prime. Let's take an example. Let's break 60 down into its prime factors. I do this by picking a factor pair for 60, except for the trivial pair of 60 and 1. It doesn't matter which factor pair you choose, the end result will always be the same. Suppose I notice that 60 has a factor pair of 5 times 12. That's my starting point for prime factoring. Now I look at the factor pair I just found. If one or both of the numbers in the pair are non-prime, then I factor the non-prime number or numbers. In this case, 5 is prime, but 12 is not. So I look for a factor pair of 12, again accepting the trivial pair of 1 and 12. Suppose I remember that 4 times 3 is 12. That's my factor pair. I repeat the process. Are any members of that factor pair non-prime? Well, 3 is a prime number, but 4 is not. So I look for a factor pair for 4. The answer is 2 and 2. 2 is a prime number, and so I am done. So I can write the number 60 as the product of prime numbers. 60 is equal to 2 times 2 times 3 times 5. This is called prime factoring. Prime factors are used in working with fractions. This is why we are learning about them now, so this knowledge will help us in arithmetic operations involving fractions. Prime numbers are also crucial to the field of communication encryption. This is precisely because finding the prime factors of very, very large numbers is extremely time-consuming, even for supercomputers. Suppose instead of giving you the number 60 to find the prime factors, I quite sadistically gave you the number 604,777 and asked you to find the prime factors. Even though 604,777 is the product of only 2 prime numbers, it would take you a very, very long time to figure out that those 2 prime numbers are 709 and 853. It would take a supercomputer a good deal less time, but I can pick a number which is much, much larger. I can choose one that is so large that it would take the fastest supercomputer years, decades, or even millennia to come up with a prime factor pair. So I can send encrypted information, say a credit card number, on a message which requires 2 keys to decrypt. The 2 keys are nothing more than very large prime numbers. I can multiply those 2 prime numbers together and transmit the resulting number in the message. Even if the message is intercepted, and even if you know that the intercepted number is the product of 2 prime numbers, it is still effectively impossible to determine the 2 prime number factors that are the decryption keys. The information needed to decrypt the message is available to everyone, but no one has the ability to solve the math problem of figuring out the prime factors. I don't need to solve the math problem because I already know the answer. I have a safe method of encryption. As a result of this, mathematicians are continuing to search for larger and larger prime numbers so that encryption can be more and more secure. They are also searching for faster ways of finding the prime factors of very large numbers. At the time of this video, the largest prime number yet discovered has nearly 25 million digits. A number of this size is, of course, much too large to write out, so it is expressed as a mathematical formula and is given the name M825-899-33.
Hey, catchy name. What public relations genius thought of that gem?
I know what you mean. This type of thing probably isn't helping much to change the public perception of mathematicians as nerds, is it?
You can say that again.
Okay, settle down.
Just saying.
You might not have understood that preceding discussion completely. The point is that the study of this area of arithmetic has applications which are far from being just academic trivia. As in this case, where we rely on encryption to keep sensitive information safe for something as simple and common as ordering products online. These principles are in active use on a daily basis. What do you think of that?
Math is so cool!
Thank you. I think so too. This is the point where I remind you that we were using the domain of counting numbers for this discussion, but the concept of multiples and factors can also be applied to integers. So when I say that 12 has 6 factors, I'm talking about 6 factors within the domain of the counting numbers. If we expand the domain to include all the integers, then -1, -2, -3, -4, -6, and -12 are also factors of 12, since -1 times -12 equals 12, as does -2 times -6, and -3 times -4. There will be applications in algebra we have yet to discuss, for example, solving quadratic equations, where it will be important to keep that in mind. We have completed another video laying down the arithmetic groundwork for higher mathematics. So give yourself a hand. Tell me what you think about it.
Whoopee!
Thank you, and have a nice day.
Hey, yous guys. Have a nice day.
We hope to see you at Veterans Upward Bound very soon and recommend a friend.